Welcome back, ladies and gentlemen. This is a video about dissociation of acids and bases here, specifically weak acid and bases. Okay, so far by now we know that there's a list of strong acids and strong bases, and here they are. You just have to memorize these. Okay, memorize that they are like HCl, HBrHI, HNO3, HClO3, HClO4, H2SO4, and the thing that makes them strong acids, they dissociate completely in water. Okay, and then strong bases, the same thing as well. They're strong electrolytes and they dissociate completely. There are 8 strong bases, basically all the metals in group 1, alkaline metals, and then 3 from alkaline earth metals with the hydroxide bases to make them bases. Okay, and so here, strong acids and strong bases will dissociate completely in water, and all other acids are considered weak. Weak acids and bases only partially dissociate. For example, HNO2 here, and it does dissociation to H plus and NO2 minus nitrite. Notice the double arrows. This double arrows tells you that it can go back in reverse. So it's going to break apart and form the acid back and go reverse at the same time. And the point at which the rate is the same going forward and backward is called equilibrium. Right here, equilibrium. Every acid base has an equilibrium constant, K, Ka for acid, Kb for base. So, just an overview here. I just want to review real quick here the difference between strong and weak acids here. For example, number 1 here, HCl. It's a strong acid. It's going to break down to H plus Cl minus. Okay? And so we're going to use this thing called a rice table. Ri is initial, C is change, and E is equilibrium, which is your N, your final. Okay. Initially, look at the question. 0.1 molar solution. 0.1 molar solution HCl. How much do we start with initially for hydrogen and chlorine? Is always going to be 0 here, because then we have the acid that hasn't broken down yet. The change. It's a strong acid, so it's a strong acid. So it dissociates completely. So we're going to lose all that 0.1 molar. And on the other hand, when HCl breaks down, you'll have 1.1 H plus and 0.1 Cl minus molar. Okay? Then we add up these two columns. Initial change here, that's 0, that's 0.1, and that's 0.1. Alright. Okay. So now the question is asking us to calculate the H plus, and this gives us the H plus right there. Okay, and that is 0.1, the final. So H concentration is 0.1 molar. So the pH is equal to the negative log of that, which is equal to 1. With that, we know that pOH is 14 minus 1 here. That's 13. Okay. And the last one. And the OH is 10 raised to the negative pOH, which is negative 13. And that's how you do that. Example 2 here. We do the same, CaOH. For the sake of simplicity, and just learn the concept behind this, and we're not going to get into a lot of the Ka1 and Kb1, Kb2 of CaOH, which is assume that it can completely dissociate completely into 2 OHs, okay? Ca, 2 plus 2 OHs. Alright. And so initial we have 0.1. There's a reaction. My columns here, I want to column here, it corresponds. This column corresponds with CaOH. This column Ca, this column's OH. Okay. So we originally start with 0.1 molar of CaOH. We start with 0 of both of those. Okay. And then the C, it dissociates completely, so it's 0.1 molar. Ca is plus 0.1. Notice it breaks up into 2 OHs, so we got to double that, so it's 0.2 molar of OH. Sorry, I forgot the plus signs over here. Alright, and then now this goes to 0, this goes to 0.1 molar. 0.2 molar. In this case, it is a base, right? This is a strong base. We know it's a base because it's got that OH. Okay, so it gives us OH. This is OH concentration. And so we have OH, we can get the POH, which is negative log of that. And that one is not as easy, so we use a handy dandy calculator. Negative log of 0.2, and we get 0.7. And so the pH must be 14 minus that, which is 13.3. Then H plus 13.3. There you go. H plus is 10 raised to the negative 13.3. And you gotta punch that in. 10 raised to the negative 13.3. And there you have it. 5.04 times 10 to the negative 14. 5.04 times 10, 5.01 times 10 to the negative 14. Okay? And that's how you find those things. Okay, to the next page. Alright, here, strong, a little bit of notes up on top here. Okay, there's different KAs. Here's the value for KA. KA is equal to, so basically KA is equal to, you see here, H plus the positive ion, the anion of the product, over the, times the cation. So the top is the product, over the reactant. Okay, the reactant is your initial, your acid concentration. Okay, and that's what Ka is. That's what the H plus means. That's what that A minus is. The cation. I'm sorry, I just flipped it backward. But it doesn't matter. I put the cation first here. And so, same thing for base. The two end product times each other over the original base amount, and you'll get your is equal to Kb. And Ka and Kb will be provided to you all the time. For example, number 1 here is an acid, so that's supposed to be a Ka. Okay, so how do you know it's an acid here? 0.1. So this acetic acid HC2H3O2 breaks down to H plus and C2H3O2. Alright, and so with this we start with 0.15 molar, and we have none of the first two. This is a weak acid, so it does not dissociate completely. In fact, only very small part, very small percentage dissociate. Very, very small. Okay? So, we don't know how much splits up. We know it's very small, so we'll just, in math or in anything we don't know, we'll call it X. We don't know how much yet, we'll figure that out. Okay? So you subtract the X there, and so that much breakup, so that much will form over here. Same thing. Right? Because they split up, they're together, they're split up, there's still 1-to-1 ratio there. So it's 1x to 1x. And so here we go. Add the columns. 0 plus x is x. 0 plus x is x for your equilibrium. Okay. So I is the initial, the start. C is the change, and is equilibrium. What is that constant when the forward and backwards is the same? Oh, I'm sorry, I forgot this. It's forward and backwards, so it's double arrow because this is a weak acid. All right, so this is 0.15 minus x. Okay, when the Ka is small, this x here is going to be very small as well. So let's take, for example, if it's 0.15 minus 0.00001, what would it be? It would be 0.14999, something like that, right? So this little number doesn't change very much, so it's really insignificant. So this number here, this x here, is negligible. So we can ignore it, and all we have left is that 0.15 molar there, and then x over here for hydrogen and x for that. Now remember, this is x for hydrogen and x for this as well. Okay. So let's fill in the Ka chart. We have Ka, which is 1.8 times 10 to the negative 5, right there, right above the table. 1.8 times 10 to the negative 5, right here. Okay. Equals the anion, which is x. The cation is x, the anion is x, divided by 0.15. We have the concentration of the acid, 0.15. So now we have to solve for this x. And remember, this x will give us our hydrogen. Okay? This x will give us our hydrogen. So we cross multiply like this. The top will be x squared, so the right side is x squared equals, and put 0.15 times 1.8 times 10 raised to the negative 5. And I get 2.7 times 10 to the negative 6. Then I have to take the square root of both sides to get my x. X is equal to, take square root, control square root, control enter, answer. I get 1.6 times 10 to the negative 3. 1.64 times 10 to the negative 3. This is our x, which is our hydrogen ion concentration. Because that's what it says up here. We can disregard, we don't need this part right there, okay? We're only looking for that H plus. We need that X though, because that's part of the products to figure out this X. So that's the H plus. You can get the pH, which is negative log of that. 1.64, so negative, times 10 to the negative 3 equals negative log, sorry, we get 2.78. Then you can get the pOH, which is 14 minus that. And you get the OH concentration by taking 10 raised to the negative 11.22. Or you can use the concentration of hydrogen and do the same thing. So 10 raised to the power of negative 11.22. So 6.02 times 10 to the 3 times 10 to the negative 12 molar there for your OH. Okay? And there's that last thing on here that it asks, the percent dissociation. Percent dissociation is simply how much the H plus, or in the case of a base, it's going to be an acid, it's OH, H plus over the original amount, which is 0.15 molar times 100. Okay? And the H amount is that. You take that, plug it in. Okay, so 1.6, 10 to the negative 3. So 1.64 times 10 to the raised to the negative 3 divided by 0.15. times 100. So I get 1.09%. And that'll answer my dissociation. Alright. A lot of numbers, a lot of steps, but that's how you do these. Alright, the same thing for number 2 here. Number 3, it's a little different. I'm just going to start on number 3 with you. Okay, number 3, it's NH3 plus H2O. This one you have to put H2O because that's the only way to get the OH. You get NH4 plus OH minus. And then after that you can disregard the H2O does not get involved in the table here. Initial, we have 0.1 molar. We have 0. And we have 0. Okay. This is going to break out a certain amount of X. This is going to add amount of X, amount of X. And we end up with X, X. And this is, again, this is negligible. So kind of zero it out. So then you end up with 0.1 here. Okay. So this is so close to 0 that it's going to be a small number. Okay, so now we just set it up KB. Remember KB, this will give us X. This time X is equal to OH. So then we'll find the POH first this time. Okay, not the pH. So I'm working through this fairly quickly. The video is getting really long, so but if you want to stop, you can stop it. If you want to keep watching for the next 3 or 4 minutes, continue. Okay, so I'm going to work through this. 1.8 times 10 to the negative 5 equals X times X over the initial, which is 0.1. Product over the initial. Okay? I cross multiply this way. Yeah, 1.8 times 10 to the negative 6 is equal to X squared. Take square root of both sides. 1.8 times 10 to the negative 6. Oops, I don't know why I did that. Square root of that. I get 1.3 times 10 to the negative 3. As my X there, that's my OH. Okay, that's my OH. This is the base, so that's my OH. And so I can get the POH by taking the negative log of that, negative log, which is 2.87. Then my pH would be the same thing, no? Close enough. 14 minus 11.12. Oh, I messed up on the other side. Should have been messed up over here. Oh no, that's right. 11.12. 11.12. Slightly different. Barely any difference. 11.12. Okay, then H plus goes 10 raised to the negative 11.12. And you go ahead and put that in your calculator and get an answer for yourself, not for me. Okay? And the percent dissociation, it's fairly easy. The percent dissociation is the OH concentration, which is 1.34 times 10 to the negative 3 over the original amount, which is 0.1 times 100%. Okay? 1.34 negative 3 divided by 0.1 times 100. I get 1.34%. Very small, and you can see that only 1% dissociate. The rest of them, they just keep going back to form the reactant. Go back to the reactant. It's reverse. So, guys, go ahead and finish number 2 and 4 then. Yeah, you'll have 2 problems to do. And then there's a sheet back here for you to calculate everything else here as well. Okay, complete this combination practice and you should be good to go. Bye-bye.